Good afternoon. This is Dr. Nakashima of Department of Plant Chemistry here at I²CNER. First of all, welcome to today's seminar. Today we have a very special guest from Yamanashi University, Professor Masahiro Watanabe. I guess all of you know him very well, so maybe a introduction is not needed, but very briefly. As you know, his career is very outstanding, and his current research field includes fuel cell study. Fuel cell include PMFC, polymer fuel cell, and DMFC, Electrocatalysts fuel cell, and PFC, and SOFC, solid oxide fuel cell. And so far he has published more than 270 original papers, and his citation is beyond 10,000. But it's quite a huge number. And he got many awards, including Mixed Minister Award, ICSJ Award, Gold Medal of the International Society of Electrochemistry, etc. And he has promoted 6 national big projects on fuel cell. As a leader since 1995, long time ago. And currently he is managing one of the biggest national projects for MFC material research. The name is Hyper FC project that lasts for 7 years. So the title of his talk today is Development of Platinum and Platinum Alloy Electrocatalysts for the Next Generation Polymer Membrane Fuel Cell. Professor Watanabe, please.
Thank you very much, Professor Nakajima, for your very kind introduction. It's my great honor to be here as a lecturer of the I²CNER seminar. As the professor introduced you, today I would like to condense my presentation on catalyst for fuel cells. As you know, the high performance fuel cell requires 3 major factors. That is high efficiency and high performance and long life. Such factors are controlled by the subjects shown here. First is relating to the mechanism, and the second one is catalyst, and third one is the structure, electrode structure, and electrolyte. And none of them is not the important. And so first we started work on electrocatalyst study. Here shows one of the example of our research relating to the anode catalyst for the methanol fuel cell or the hydrogen CO containing oxidation reaction in a fuel cell. And we found discovered bifunctional mechanism of the alloys among the platinum precious metals. And also we found electrocatalysts by the other atom. The alloy catalyst shows almost similar catalytic activity between the bulky alloy and just one monolayer catalyst. And one of the papers cited from the published time to now, and this catalyst, platinum lutetium alloy, only one catalyst used commercially in NFM and direct methanol fuel cell so far. And this is the modern type fuel cell introduced to my house last year, together with solar cell. So my house electricity covered both of the power source. And recently, we also developed a new catalyst, which are alloys of platinum with non-precious metals, in order to reduce the amount of the precious metal installed to the fuel cells. And this work was done by my student, about 10 years ago, and cited very frequently, because this phenomenon is very interesting due to the electrocatalyst structures. The non-precious metals are leached out from the alloys, but remain skin layer on the surface, and such skin layer shows very nice catalytic activity as shown here. The activity enhanced by 10 to 15 times from that of pure platinum. And all of our research work cited very frequently recently, particularly after 2000 years. Nowadays, beyond the 12,000 times are cited now. And probably such the steep increase of the citation is related to the enormous interest of the polymer electrolyte fuel cells, which has various application area, starting from the aerospace to deep sea, from aerospace and deep sea, and to the residential applications, cogeneration system, or power source for the electric car or robot power source, and also the application to the leisure or portable electrode devices. But in order to expand the application area to the wide in the 2020s, there are still essential problems to be solved. For example, cost reduction, reliability improvement, infrastructure construction, or international standardization of the parts systems and evaluation method. The cost reduction can be achieved by reduction of platinum loading to 1/10 or reduction of PEM cost to 1/20, and also the improving the MVA performance with lowered platinum loading by using such a electrolyte membrane. And also the reduction of the separators cost is important. Relating to the research, the clarification of the degradation phenomena or enhancement mechanism is important. We are working on a research subject shown the pink color here. But today, I'd like to condense my presentation on the reduction of platinum loading to 1/10. Here shows the outline of my presentation. First, the enhancement of platinum activity for oxygen reduction reaction by nano-sizing and alloying with transient non-precious metal, because the mass activity shown by the multiple of specific activity and specific surface area of the catalyst. And the second is the assignment of the oxygen species relating to the reaction at the polycrystalline platinum and platinum 111 surface, and domination of their coverage with electrochemical XPS systems. Third, the proposing presumable oxygen reduction mechanism on platinum alloys as a clue for new catalyst design. And fourth, preparation of highly dispersed alloy catalyst and an approach to the durable catalyst. First, the development of high performance oxygen catalyst by increasing the specific activity and confirm the enhancement effect by dispersing platinum on high surface substrate. But we need to answer to the question, so-called particle size effect, is true or not for at the oxygen reduction. So here shows the electrocatalyst which used for the experiment. Here shows the three types of catalyst which has different particle size, about 1.4, 2.2, or 3.8, or some other catalyst, which shows size distribution shown here. And also, we developed the channel flow double electrode method, which allows us determination of the kinetically controlled current and also the yield of the byproduct over wide temperature range, from room temperature to beyond 100 degrees Celsius in a closed system under low electric noises. The cell has a very narrow gap, less than 0.5 millimeter, and electrode placed here. The size is 1 millimeter, 1 centimeter, very small size. And electrolyte which were dissolved oxygen or some other reactant in the electrolyte flow over the catalyst surface. The working electrode consists of bulky platinum or sputtered platinum or platinum precious metal alloy, a non-precious metal alloy, and also the naphthalene coated supported platinum or platinum alloy on a carbon support, as shown here. And byproducts are also detected at the collecting electrode. The relationship between electrolyte flow rate and current density are correlated with these Leibniz-Kutek equations, flow rate and current density. And by extrapolating the flow rate to infinite values, we can get the kinetically controlled current by using the observed current. And also we collected the change of the concentration of the oxygen or a proton concentration in the electrolyte together with apparent surface area of the electrode, so that we can get the kinetic apparent reaction constant. They are plotted into the Arrhenius relationship. As you can see, all of the different size catalysts rate constant fall into the same regression lines, and that these are also consistent well with the bulky platinum catalytic activities as shown here. So it is clear the catalytic activity has no particle size effect, and activity can be increased in proportion to the specific surface area. And also we found that if the operation temperature of the cell increases from the conventional the 80 degree to 110 degrees Celsius, we can get much higher catalytic activity as shown here. And the second topic is enhancement of the specific activity by alloying platinum with transient non-precious metals. Here shows enhanced oxygen reaction at various platinum and different transition metals. As you can see, we can get, we can get the higher catalytic activity like this. But as shown later, however, it was found that the platinum skin layer is formed on the alloy surface at the initial stage of the oxygen reaction measurement, but still exhibit as such enhanced activity compared to the bulky platinum or bulky pure platinum. Oh, I forgot to explain the preparation of the catalyst. In this case, we prepared the alloy catalyst by the sputtering method using the two target. And here in the after, we pre-treated such alloy catalyst in order to get the stable surface states by electrochemical the potential sweep method, which calls the electrochemical annealing. And here shows the relationship, the kinetically controlled current versus the non-precious metal content in alloys. As you can see, by the alloying with nickel, we can get about 10 times higher activity and 14 times, 20 times higher activity from that of bulky platinum at different compositions. This is the first observation of the composition-dependent enhancement by platinum skin underlined with platinum non-precious metal alloys. And so we proposed temporarily proposed the hypothetic mechanism for the enhancement of the oxygen reduction reaction relating to the modification of the electronic structure of the skin layer of platinum. But I will discuss in details later using the XPS data about the mechanism. And we also studied about such non-precious metal, platinum non-precious metal alloys behavior by using the electrochemical quartz crystal nanobalance or microbalance. During the electrochemical cycling, first stage we observe some oxidation current relating to the dissolution of some component. And but the cyclic voltagram finally reached to the stable condition shown by red color. And mass change observed first stage, but finally reached the same as some stable conditions. This the electrochemical, the hydrogen adsorption, desorption charge plotted as a function of the number of potential sweep. As you can see, it doesn't change much and shows the steady values. And mass loss occurred at the first stage, but finally reached to the stable states. And analyzing this mass change and also the amount of the ions dissolved in the electrolyte, we could estimate, or we could conclude the formation of the platinum skins on the alloy surface, which has a thickness of about 1 nanometer. But we are not sure at this stage whether the surface is a skeleton structure or not. So next stage, we use the STM system to observe the surface states. Here shows the spattered electrode surface pictures observed using the STM on a platinum iron alloy surface. And after immersing the catalyst into the acid electrolyte, we observe the drastic surface morphology change just after the soaking. But after maintaining the potential constant or cycling, we observe the morphology change, and the surface shows self-smoothing phenomena. And after sometimes later, we observe the very clear the step and terrace the structure on the surface. And focused the surface structure shows the nice spot shown here, which structure corresponding to the platinum 111 1 by 1 times 1 structures. That means the surface platinum atom are rearranged on the surface and makes a very well-packed the surface protecting structures. It is not the skeleton structure, but the flat surface. And in spite of the formation of the platinum skin layer, just pure platinum skin layer, that property is completely different from the bulky platinum surface, as already I showed you. And so the next day we try to examine the electronic structures of the such a platinum skin surface. This shows the D-band structure change by alloying the platinum with cobalt or leucine. As you can see, Fermi level area a little bit changed, and Fermi level, D-band center shifted to the higher energy direction, but it is not be dealt with quantitatively. So we checked about the core level shift by alloying, and we observed clearly the change of the energy level from pure platinum to the alloy skin, the alloy surface. There is a core level shift. So it is clear chemical shift. This phenomena can be explained as pure platinum is alloyed with the transition non-precious metals, for example, cobalt. The electron transferred from cobalt to platinum D-band. Since the XPS system adjusts the the Fermi level to the ground level, so the by shifting the D-band center, same time we can detect the clear core level shift. And this core level shift is well consistent with theoretically estimated values like this. And after electrochemical annealing, we observed very small shift of the binding energy at the skin layer surface. So platinum skin on the alloy surface exhibit a positive shift in platinum core level as well as the D-band center compared with pure platinum. And even particularly the stable platinum leucine alloy, we observed almost no change of the core level. And so here shows the core level shift of platinum alloys before and after electrochemical stabilization. Core level shift increases in proportion to the content of the second metal. Sorry. Like this. And even after the electrochemical annealing, still the chemical shift remained. But the maximum was observed at around 0.5. This is probably because at the high non-precious metal content, the surface is not so stable. So the thicker platinum skin might be formed on the surface. So shows the decrease of the chemical shift. But anyway, then we tested the catalytic behavior using the double electrode method again. and clear the enhancement was observed, as I already showed you. And this enhancement kept not only the room temperature, but also the elevated temperature, as shown here. It is about 2 to 4 times higher, but without changing the slope of the RNS plot. That means the activation energy, EA, in the RNS equation doesn't change, but the change at the Z value, the pre-exponential values. So we expect such a Z values increase strongly suggested the increase in oxygen coverage on the surface, which are relating to the oxygen reduction reaction. So we now intend to try the assignment of the oxygen species at platinum, polyplatinum, and also the single crystal surface, and the determination of the oxygen coverage. And we established we made the electrochemical chamber attached to the XPS system. And we use electrochemicals in the systems. We use 0.1 molar hydrofluoric acid HF solutions, dissolved nitrogen or oxygen, and test electrode were prepared by sputtering the pure platinum or platinum iron or platinum cobalt, and pre-treated the surface in an electrolyte to form the stable platinum skin layer. And each test electrode was polarized at a given potential here. For 5 or 15 minutes in nitrogen or oxygen saturated solution, respectively, followed by immersing from the solution under the potential control. And then the electrode was transferred to ultra vacuum system and taken XPS within 5 minutes. Here shows the potential sweep curve and also the O1S spectra for pure platinum after immersion in nitrogen purged solution. As you can see, in a so-called double layer region, we detected the 2 types of the oxygen species around here. And in a so-called oxidation area, we observe another oxygen species. By increasing the potential. Similar spectra are also observed in a double region at the single crystal electrode, like this, and second peak area, we observed another oxygen species here. And second oxygen peak area, we observed further oxygen species. So then we deconvoluted the adsorbed species into different peak. The first two are correlated to the water adsorbed on the surface. Which are strongly adsorbed first layer water and hydrogen bonded second layer waters, green and blue. And another one assigned to OH species and O species, which binding energy are well consistent with those observed in ultra high vacuum published data. Here shows the potential dependence of the 1O1s binding energy and coverage of the each assigned O species in nitrogen saturated HF electrolyte solution. As you can see, nearly no dependence of each binding energy position on potential. And OH species, orange color, start to increase at 0.6 volt, accompanying the increase in water molecule, and exhibit a level of with decrease of water after this single crystal peak 1. And all species increase at 0.8 volt or beyond 8 volt with decreasing OH species. In a potential region higher than 0.9 volt, successive oxidation indicated are indicated as shown here. On the polycrystalline electrode, both not only the single crystal but also the polycrystalline exhibit almost no potential dependence in each binding position. And platinum 111 and polyplatinum shows a different potential dependencies at the formation of the surface oxide that is successfully at the former, but simultaneously at the latter. So different phenomenon. Thus, we first directly assign and quantify the all species on peak 1, peak 2 on a single crystal surface, and peak 3 on a polycrystalline surface. Beyond the 0.2 volt, both OH and O species level of as shown here, but in this region, another oxygen species increased, which are assigned to the bulk oxide oxygen species of the platinum. Actually, we detected the oxidation signal of platinum on the platinum 4F energy levels like this. That is shown. This is the surface OH or O species, and this is oxygen species at such a potential region. And now we propose the presumable oxygen reduction mechanism on the platinum alloy as a clue for new catalyst. In the similar manner, we determine the oxygen coverage on the platinum skin layer and also the pure platinum surface in a oxygen saturated electrolyte solution in comparison with the nitrogen saturated solution. The oxygen coverage at the platinum skin surface is much increased by additional oxygen adsorbed species from that of pure platinum, indicating the enhanced dissociative adsorption from the molecular oxygen, presumably adsorption to platinum site free from strongly adsorbed original the surface oxide. And so now that we discuss about the mechanism, enhanced catalytic activity shown by this equation. The enhanced oxygen coverage at the platinum skin layer compared to pure platinum should be ascribed to the electronic structure modified by that of underlying alloys. And the increased oxygen species are clearly correlated to the increased Z values. And thus we propose below enhancement mechanism for oxygen reaction at platinum skin surface. That is enrichment of the limiting reactant O species for the slowest elementary step and resulting in the higher total reaction rate. Now, we discussed the mechanism of the enhancement by alloying platinum with non-precious metal. Now, we try to prepare the practically usable, highly dispersed platinum and the alloy catalyst, thus designed for an approach to the durable catalyst. We have developed a new preparation method of size-controlled platinum-based catalyst called the nanocapsule method. The platinum precursor encapsulated, such a precursor encapsulated into the micelles, nano-sized micelles, and reduced with reducing agent in the capsule, and supported on the catalyst support, such as carbon black or graphitized carbon black. And finally, removes the nanocapsules. We have succeeded to control the particle size only by changing the molar ratio of metal precursor to surfactant in the preparation. As you can see, by changing the ratio, we can get the different particle size with a very narrow size distributions. And also, we succeeded to prepare the platinum-based alloy catalyst with well-controlled particle size and compositions and loading level as shown below next. This is platinum alloy, platinum 3 and cobalt supported on carbon. As you can see, 2 nanometer, 3 nanometer, 4 nanometers catalysts are uniformly dispersed on the carbon support compared to the commercial one. Commercial one has a small and big particle with a very wide size distribution. And also the composition well controlled. In this case, the platinum 3 cobalt. As you can see, the ratio of the component are well consistent with the original the precursors ratio without the regardless the particle size and the size composition distribution is very narrow compared to the commercial catalyst. So such we already possible to prepare any type of the catalyst, alloy catalyst and size. Now I like to show you the catalytic behavior of the different compositions alloys dispersed on the carbon support. Here shows the 3 component catalyst, 3 composition catalyst: platinum, cobalt 1:1, 2:1, and 3:1 ratio. And in this case, also the size are well controlled compared to the commercial one. And here shows the RNS plot at the different catalytic activity. As you can see, the platinum 3 cobalt shows the highest catalytic activity, but the all alloy catalyst shows the degradation of the catalytic activity at a higher temperature region. But this composition is most active and most stable, at least until 80 degrees Celsius. So by this nano-size experiment, we could confirm the alloy catalyst shows superior catalytic activity compared to the bulky platinum. But the problem is still the stability is not enough. So we are now working on stabilizing the skin layers much more from that of the electrochemical the annealing or some chemical annealing process, but the new method. And now the stable region expanded to 110 degrees Celsius. Not here now, but so we believe that we almost reached to the practical catalyst preparation. And finally, I like to show you the benefit of the nanocapsule method catalyst in the viewpoint of the durability in a practical operation condition. As you know, during the start and stop cycling, the fuel cell catalyst degrade drastically because of the carbon corrosion and peeling off the supported catalyst from the carbon support or coagulation of catalyst particle on the carbon support because of the instability of the support. So recently, the people are using the graphitized carbon as a support. So here we tested our catalyst to get, in comparison with the commercial catalyst by using the the start and stop cycle simulating potential cycling shown here. 0.3 volt 30 minutes and 0.9 volt 30 minutes, repeating these cycles on the each catalyst, and measure the specific surface area and also the catalytic activity for the oxygen reduction reaction at room temperature to 80 degrees Celsius. Here shows the catalyst for temp and size distribution at on the commercial carbon black supported catalyst and graphitized carbon support catalyst and nanocapsule catalyst. At the commercial carbon black support has a very high surface area, so the platinum dispersion is easy and forms a very nice phase. But the low surface area carbon support, even the commercial one, has not good distribution of the catalyst. Only the step site or such a place more catalysts are observed. But by our method, even the same using the same carbon support, we can get a very nice particle distribution on the surface comparable to the commercial high surface area carbon. And the particle size are almost same. Then such a carbon support has a different crystal structure. So this is more stable compared to the one. But anyway, this shows temperature-dependent oxygen reaction activities on first the commercially carbon black surface. And next, the blue one shows the commercial graphitized carbon. The catalytic activity is about 2 times less activity. But the nanocapsule catalyst shows almost the same catalytic activity as that of the commercial carbon black support catalyst. And this shows the change of the mass activity at a different potential as a function of the potential cycling. The commercial catalyst shows quick decrease of the catalytic activity by the cycling due to the corrosion. The graphitized carbon black shows lower catalytic activity initially, but much stable than that of the commercial carbon black supported catalyst like this. And how about the nanocapsule catalyst? The initial catalytic activity is very high and shows a very stable the catalytic behavior, as you can see. The mass activity plotted to the logarithm of the cycle number. Then we found the activity decreased in proportion to the logarithm of the potential cycle linearly. So surface area also shows similar behavior. And this is a picture after the potential cycling. after 5,000 cycles, both the commercial carbon black catalyst and graphitized carbon shows a very big change of the supporting catalyst. But our catalyst shows a very nice phase, even though the particle size grow. Now, why we can get the lower catalytic activity at commercial graphitized carbon? The platinum probably was overcrowded on the carbon, graphitized carbon surface, particularly edge side, and particle growth was accelerated by the agglomeration by the near side, and oxygen activity was decreased by oxygen diffusion layers overlapping. But at the well-dispersed nanocapsule catalyst, particle agglomeration was mitigated due to the sufficient intercrystal distance. The high oxygen activity can be achieved, maintained, because of the no overlapping of the reactant diffusion layers. So I showed some of the approaches to increase the catalytic activity and reduce the cost of the catalyst for the large fuel cell market. And how the reduction of the platinum catalyst used can be achieved. It is shortest and best and most practical approach is reduction of the platinum of catalyst used. And how to reduce the, how to achieve the 1/10 to 1/20 reduction. That is ippon with awasewaza in judo rule. How? Alloying platinum and non-precious metals and get the few times higher catalytic activity. And nano-sized catalysts, they are few times higher activity. The effectiveness of the MEA a few times, and the high temperature operation a few times, and synergy effect of the catalyst with support a few times, and the optimization of the operation made, operation mode a few times. And finally, we can get 2 to 6 order to 3 to 6 order times higher. So easily we can achieve the such values. That is my strategy. And my opinion about the strategy for fuel cell development future. The first, we should achieve the realize the fuel cell car or NFM by using the acid electrolyte and precious metal alloys. And next stage, for the much bigger market, we need to develop the alkaline type membrane and non-precious catalyst, and realize the hydrogen energy society. in the future. Finally, I'd like to express my acknowledgement to co-workers on these topics. And this work was supported by Fund for High Performance Fuel Cell project from NEDO of Japan. And finally, I very much thank you for your very kind attention. Thank you very much.